welcome to CPFD's Getting Started with Virtual Reactor 24.0 webinar. My name is Rosemary Clark, and I'm the Senior Support Engineer for Barracuda Virtual Reactor. I'll be your host for today's webinar, and CPFD's Sam Clark will be our presenter. We're excited to have the opportunity to tell you about the new features and enhancements included in our version 24.0 release. This webinar is being recorded, so if you miss anything or you want to share something you saw with a colleague or a friend, you will be able to do that. The recording will be posted on our website's webinars and presentations page under the resources tab. And this webinar should be posted there in the next 48 hours or so, so make sure you check back then to view the recording. We would like this webinar to be interactive, and we need your help to make that happen. As you think of questions, please put them in the question panel. We have intentionally allocated a significant amount of time to answer questions after the presentation, and it will help us to stay organized if you put in the questions as you think of them throughout the presentation instead of all at the end. And for those of you joining us today who are new to CPFD software, let me briefly introduce our company. Here at CPFD Software, we are advancing multi-phase simulation and technology for fluid particle systems, primarily fluidized bed reactors. Our Barracuda Virtual Reactor software product models the 3D transient hydrodynamics, heat balance, and chemical reactions in industrial units. It is typically used to improve the reliability and performance of these systems through simulation. And these are often industrial units that operate 24/7 for quite possibly years on end. For operating units, virtual reactor simulations allow you to look inside the system in a unique way, determine root causes of underperformance, and use virtual testing to reduce the risk of making any changes. And often, as you're looking at the software results, other ideas come to mind and additional optimization opportunities are identified. For those of you developing new technology, Barracuda is used to accelerate and broaden that R&D and then quickly commercialize, scale up, and communicate the unique capabilities of your technology to customers, partners, and others. Now let's get into the webinar itself. Our presenter today is Sam Clark. Sam is the Barracuda Virtual Reactor Product Manager and has been at CPFD since 2008. He has worked in a number of areas at CPFD over the years, from software testing to engineering service projects to customer support and training. In his current role as product manager, Sam works closely with CPFD's development team to design features and capabilities for virtual reactor that benefit our customers all over the world. And I'll turn it over to you now, Sam.
Great. Thanks for the introduction, Rosemary. And thank you to everyone who's joining us for the webinar today. The development team here at CPFD is proud to release Barracuda version 24.0, which has a number of great new features. If you're a Barracuda user, you should have received our release email earlier this morning. If you didn't, please let us know and we'll add you to the email list for future release announcements. Version 24 is available for download on the CPFD support site now, so please log in and check it out. You can find more details about all the things we'll cover today in the release guide chapter of the user manual, along with links to the full documentation sections in the manual. As is our tradition here at CPFD, we will go through a lot of the new features in this release by their order in the GUI. And so the GUI has a tree along the left side, and what we'll do is we'll cover these features in the order that they would appear in the tree. Okay, so the first new feature that we'd like to highlight is time-varying gravity and specifically rotating about a major axis. And so this is a feature that was previously in beta mode of Barracuda, and this has been in beta mode for I think about a year. And so you may recognize this animation that we're showing on the right-hand side here of a rotating cylinder with some wall surfaces that are agitating the particles as the gravity vector is being rotated about the central axis of the cylinder. And so now this feature has been moved out of beta mode, so it's fully supported and fully documented. And so for people who have this type of system, I hope that this is a very useful feature to you. The way that this works is that the domain itself is not actually moving, but the gravity vector is being rotated, and so then we can get the effect of a moving domain. However, it does have a couple of limitations, and so our recommendation is that you would not use this for very fast rotations, but rather kind of slowly rotating drums as we're seeing here, right? It doesn't have centrifugal forces or things like that that might be necessary for really fast rotational velocities. One thing to note is that when you use this feature, when you make an animation in TechPlot, we do have a helper script called rotating gravity animation. And we encourage you to use this. What it will do is it will connect to a running TechPlot session, and it will rotate the view as the solution time progresses, so that you can get an animation that corresponds to the rotational velocity that you've specified. The next feature we'll talk about is kind of similar, but it's a little bit more general. And so this is time-varying gravity using a transient file. And this follows the same pattern as other SFF files throughout the Barracuda GUI, where the first column is time, and then the second, third, and fourth columns are the X, Y, and Z components of gravity. And so by using this type of SFF file, you can do very general and flexible gravity adjustments as your simulation is running. And I'll show an example of that on the next slide. This also has kind of a companion helper script. This one's called time varying gravity animation. And what this does is it reads the SFF file and it connects to a running TechPlot session and adjusts the view according to what's happening in the SFF file. So hopefully that's a useful feature for people who are doing these types of simulations. The example that we have here is kind of a fun one. And so what would happen if you put your Kuiper's training problem on the NASA Vomit comet? So here at about 10 seconds, we're going to start going up in our 45-degree ascent on the Vomit comet. And if you're not familiar with this, it simulates zero gravity when it gets to the top. And so we're about to hit that here. So all of the particles have now kind of floated to the top. We have a few stragglers. Now we're going back down into our 45-degree descent, and then we'll quickly get to flat flight again. And so this is kind of maybe a silly example. I don't know if anyone's ever put a fluidized bed on a zero gravity flight, but we thought this would be kind of an interesting way to highlight how this general time varying gravity feature could potentially be used. Okay, I will go ahead and move on to the next feature. This is also in the global settings window, and what you'll see is we have added a new mode of heat transfer that was previously not available, and this mode is particle-to-particle thermal conduction. This can also be applied to bubbles, so just be aware of that. The wording that you see on the screen right now is for compressible simulations that only have particles with solid or liquid materials. But if you have bubbles in your system, this can also be used. The conduction is based on material properties that you define for any materials on the particles or the bubbles. And then it is calculated in each computational cell at each time step. And so if you use this, just be aware that you will see information available on the cells when you do some post-processing that hasn't been available previously. But yeah, just be aware of that. The other thing about this is that really what you want to be careful about is to use this feature only if this mode of heat transfer is really important, because it does add a little bit of computational time. So just be aware of that. Often this is kind of negligible for well-fluidized beds. If your particles have very short contact times, then conduction is usually not nearly as important as convection or radiation. So the default setting is off in the GUI because a lot of Barracuda users are doing fluidized bed type of simulations. However, if you do have something like a packed bed or some other system where the particles do pack closely over long timescales, then this mode of heat transfer can be important. And so that's why we have added it to the product. The next feature I'll point out is a few updates to evaporation models. And this was released maybe 2 or 3 versions ago in Barracuda, where you could have a material that's a liquid and a vapor, or there are 2 phases associated with the material. And the liquid can evaporate into the vapor phase, and the vapor can condense back onto the liquid phase, usually when you have a liquid on a particle surface. And so the improvements that we've done here, or the updates that we've done, are a little bit better validation of the enthalpy and heat capacity expressions. And our goal here is to just make it easy for users to know if their base material properties are physically realistic and valid. And so you might see a few more warning messages if you have enthalpies that are going negative, for example, or heat capacities that are going negative, I apologize. And so you'll see when you plot your enthalpy curves, now both the liquid enthalpy curve and the vapor enthalpy curve will be plotted together. So that should make it a little bit easier to just make sure that these are consistent with each other and that the material properties look good. The other thing that we've implemented are several stability terms on the solver side of things. And so these should help evaporation calculations to run more smoothly and simulations to be more robust when you're using evaporation. Another feature that has been added, or an option, is what we're calling directional momentum redirection. And so this is a new option in the particles main window. And what it will do is it influences how particles behave when they approach regions of closed pack volume fraction, or when a whole block of particles is at closed pack. And when you choose the directional option, the behavior will be such that the particles will always move in the direction of decreasing particle stress. And so this is different than previous versions of Barracuda, where the direction of particle movement had a random component to it. And so based on our testing, this has been a well-performing option. What we're seeing here on the right-hand side are several piles of sand, where we started the pile of sand at close pack in the middle, and then we were seeing what angle of repose it would form over time. And so if you vary the parameter that's called maximum momentum redirection from collision, this can go anywhere from 0% to 100%. What we found is that this can correspond quite well to the angle of repose. And 40% is generally a pretty good value for typical sand-like materials. And so if you change this value, you can have some influence on what that angle of repose will be. And we've also found that this can help when particles are in a system that has angled surfaces, when you want particles to flow down an angled standpipe, for example, or an angled wall of a vessel. We found that using this option can be helpful in those cases. Okay, the next change that I'll point out is a new way that we've started managing particle species numbering if you delete a particle species from the middle of a list. So just be aware, what I'm showing here is the old behavior, and this is version 23.1. In this version and previous, if you had a list of particle species and you deleted one from the middle of the list, you would see that the GUI would leave a gap in the numbering. And this would cause a problem when you started post-processing things with TechPlot, because when we output this data to TechPlot, we always ensure that the numbers are exactly in order without any gaps. And so the numbering could be mismatched between what you see in the GUI and what you see in TechPlot. And so this could cause some confusion. You always had to keep track of really what index you were on. And so we decided to change this behavior, so just be aware of this. In version 24 and moving forward, if you were to delete a species from the middle of the list, now the GUI will make sure that these species ID values are contiguous and that there are no gaps in those values. And so the motivation here is that now when you look in TechPlot, the species ID numbers in TechPlot are guaranteed to match the species ID numbers that you see in the GUI and also that you see in raw particle data files either from the regular raw particle data or from flux planes. And so our hope here is that this just makes post-processing a little bit less confusing, a little bit less error prone, and helps to avoid any confusion there. Okay, let us continue. So this is a new capability that we've added to BC connectors. And this was a feature request from several users where they wanted to be able to more realistically and dynamically communicate information between locations that were connected by BC connectors. And so the goal is if the pressure is changing in one location near the outlet of a BC connector, they wanted to communicate those pressure changes back to the location near the inlet. And so we've enabled that. And this one's a little tough to show just through screenshots, so I will show this during the live demo portion in a few minutes, and we'll try to explain kind of exactly how to configure this and what the intention is. When you use this feature, you can also specify a pressure drop across the BC connector, and so that could be helpful to more realistically simulate some systems. A chemistry-related feature that we've added for this release is dealing with how heat is distributed from volume average chemical reactions. And so this mode of automatically calculating how much heat goes to the particle phase versus the fluid phase, this is actually already how discrete reactions have been working for several years now. And what we've done is we've added the same sorts of calculations to volume average reactions. And this should make chemical reaction simulations more realistic. It will help to avoid extreme fluid temperature fluctuations. In previous versions, the default was that all of the heat should go to the fluid phase, and then it had to transfer to the fluid phase through, or to the particle phase through convection. But now it doesn't have to do that, right? Some portion of it will automatically be distributed to the particles, another portion automatically distributed to the fluid, and hopefully just make these sorts of simulations a little bit easier to run and more robust. Another feature that we've added is something that we hope will make SFF files a little bit more convenient to use in certain cases. As current Barracuda users are probably well familiar with, the traditional behavior of SFF files is that you can vary a parameter over time. And let's take, for example, mass flow rate here. So we put these entries in the SFF file, and the mass flow rate changes from 2 kilograms per second to 5 kilograms per second over the first 5 seconds of the simulation. And the way that this has always been done is it changes in an interpolated manner. And the nice thing about this is that it gives you smooth changes and you don't get big shocks to your system. So, you know, there are some advantages of this. However, sometimes you really do want kind of step changes in the behavior. And in the past, you would always have to put extra rows in here to kind of approximate step changes. And so now what we've done is we've added this checkbox so that you can either enable or disable interpolation. And so this should make it much more convenient to get step changes if that is the desired behavior that you have for your boundary condition. The final Barracuda GUI feature that I want to point out is related to monitoring your simulations. We've added a new button on the run window of the GUI, and this button is called Monitor Run. And what it does is once you start running a simulation, you can click this button, and it will automatically create a number of plots from history.log, runtime.log, and memory.log. And then it also has the capability to refresh and reload as the simulation is running, so that you can just conveniently keep an eye on a number of parameters that are usually important for most Barracuda simulations. So I'll demonstrate this in the live demo portion as well to show you kind of the anticipated workflow for how we think this will be convenient to use. The final update is that we like to keep up to date with the latest version of TechPlot 360. And so you'll see in this release of Barracuda, we've moved up to 2023 R2. Excuse me. This release I don't think it has anything that's a major change for most Barracuda users. However, if you're interested in seeing what's new, make sure you take a look at this webinar, and we'll make sure and have this link on the page of the webinar recording so it's easy to find. But yeah, TechPlot did do a webinar where they showed what is new in this version. Okay, at this point, I'll go ahead and drop out of PowerPoint. And so now you should be seeing a Barracuda GUI on my screen. And what I have here is an example showing how the BC connector pressure feedback feature works. To give you an idea of what this is trying to do, I'm going to go ahead and view the setup for this case. And TechPlot should open up here. Okay. And just to give you a brief kind of explanation of how we're going to look at this feature. This example has two independent fluidized beds. We're calling the top bed Reactor 1, and we're calling the lower bed Reactor 2. And particles are transferred from the outlet of Reactor 1 to the inlet of Reactor 2 through kind of a regular BC connector. And then the other BC connector is intended to take the fluidizing gas that's being injected at the bottom of Reactor 2. It will take that gas and use it as the fluidizing gas of Reactor 1, and it will also communicate any pressure changes from Reactor 1 back to Reactor 2 with a pressure drop. So just keep that in mind. That's what we're trying to do with this particular setup. I'll go back to the Barracuda GUI and just kind of walk you through how this would be configured in the GUI itself. So this is our pressure BC at the top of Reactor 2. And what you'll see here is if you go to the Fluid tab for a pressure BC, you'll now see a checkbox that says Use BC Connector Pressure. And so if you choose this option, what you are telling the GUI is, okay, I'm going to give you a pressure value, and this is my initial pressure at this boundary condition. But after the solver starts running, don't use this pressure, use the pressure from the BC connector. So we'll get our pressure information from that. And then if you go to the BC connector itself, we'll edit this BC connector. And what we'll see is that the Reactor 2 top outlet pressure BC is here on the left, and the Reactor 1 fluidizing gas, which is a set of injection BCs, is on the right. So this is the outlet from our BC connector. So if I double click that, we'll see that there's also a new checkbox here that says include in pressure feedback. And so there is a little bit of flexibility, right? If you had multiple boundary conditions feeding back into this BC connector, you could potentially exclude or include just certain ones from that set. But in this simple example, it's just kind of one-to-one. So we'll check that. And then there's also a pressure drop button in the middle where you can say, okay, what is the pressure drop that I should impose from this outlet back to this inlet? And so this is kind of a familiar pattern as well. You can either specify a value and then it's stuck that way for the entire simulation, or you can do an SFF file and you can vary the pressure drop over time. So that's what we're demonstrating here, is just using an SFF file, time versus pressure drop. Okay, and this simulation has already been run, so I'm going to go ahead and do a quick view results so that we can see how this looks. Okay. So we can see here both of these beds are fluidized, and the fluidizing gas from Reactor 2 is going up through this pressure BC. It's being transmitted back to Reactor 1. And to see the effect of this pressure connection, let's look at cells colored by fluid pressure. And so this is in line with what we would want based on the pressure drop that we specified, that Reactor 1 should overall be at a lower pressure than Reactor 2. And I've also saved a layout file that shows kind of quantitatively what this looks like. Okay, so here, during the setup of this model, I put a data point at the bottom of Reactor 1 and a data point at the top of reactor 2 so that we could easily plot what's happening in terms of those pressure values. And so we can see that the reactor 1 bottom is around 110,000 pascals. And I'm going to try to make this thing redraw itself. Okay, the fonts are a little better now. And then the top of reactor 2 is at about 120,000 pascals. So there's this 10,000 pascal difference. And then also the pressure fluctuations at reactor 1 are communicated back to the top of reactor 2. So that pressure VC is dynamically changing in response to what's happening at the bottom of reactor 1. So that's the overall idea of what we're trying to do is enable this sort of communication of that pressure information across the boundary condition connector. Okay, I'm going to go ahead and minimize that, at least for the moment. And I wanted to demo how the monitor run feature works. So just to show this, I have our supplemental training problem, which is a small cyclone, and it's just kind of set up and ready to run. So I'm going to go ahead and click Run Solver. And we should see that this starts up, and this is a relatively small simulation, so it makes it a little bit easier to see how this feature can be used in a convenient manner. Once your solver starts running and has written some data to history.log and runtime.log, in the run window of the GUI, you can click the monitor run button. So I'll go ahead and do that now. And TechPlot should open up here with several plots from these files. Okay, there we go. So we can see at the current time when I click that button, the simulation was at about 0.13 or 0.14 seconds of time. And these are the plots that you would get from clicking that button. So first is your time step, then your CFL, then your particle mass in the system, and the number of clouds in the system. And so these are pretty commonly needed or useful plots from history.log. This plotting strategy also makes use of what TechPlot calls pages. And if you haven't used pages before, you may not see this little sidebar in your TechPlot window. So just be aware of that. If you don't see something called pages, go to View and make sure that the Pages sidebar option has the checkbox next to it. And then you can put this little dialog wherever you want within the TechPlot window. But the idea here is that the first page is history.log. If I click on the second page, it'll switch over to runtime.log. And this plot will show me how much time has elapsed in my simulation, what is my current simulation speed, how much time does the solver think it needs to complete the simulation. So there's an estimated time to completion based on the current simulation speed. And then there's also something called a balance factor. And this will really only matter for people who are running in multi-GPU mode. And it will show you how well balanced the GPUs are in terms of how much data they each have. And then finally, there's a memory.log plot. And for some people, this isn't horribly important, but as you start getting to larger and larger simulations, this can become important. So that's why we put it here. This simulation is relatively small, right? It's about 500 megabytes or half a gigabyte. But often Barracuda simulations could be something like 10 gigabytes or 20 gigabytes. And so keeping an eye on the overall size can be a useful thing to do. I'm going to go back to history.log. I'll make this a little bit smaller so that we can see it next to the run window. So at this point, my simulation has made it out to 0.25 seconds-ish. And so if I go over here, there's a quick macro panel item called Refresh Reload Barracuda Data. And if I click that, what we'll see is that all of the plots on all of the pages automatically read in any newly available data, and they update the limits on the plots. And so pretty convenient to just leave this TechPlot window open. It should not take up much memory. We're not showing three-dimensional results or loading in huge TechPlot files. So you can kind of leave this sitting there while your solver is running, and then you can do refresh reload and get a quick update of these plots that are included. And we would certainly love to hear any feedback that users have on this. Is this a convenient way to do it? Are there any other plots that you would really like to see all the time? That sort of feedback would definitely be of interest so that we can try to make other things convenient in this same sort of way. Okay, I think those were all the things that I wanted to demo at the moment. So I'll go ahead and switch back to presentation mode and hand things back over to Rosemary.
All right. Thanks, Sam. Okay, so now we've covered all the new features in Barracuda version 24.0 that we're going to talk about today. So now is a great time to submit your questions if you have any, and then we'll be answering questions at the end of the presentation. So be sure to get yours in the question panel. For those of you that are new to CPFD software, I just want to briefly let you know a few different ways that you can get started working with us. Software licensing is the first method, where your team uses Barracuda directly to set up, run, and post-process simulations. And we have a number of different licensing options available, so please contact our sales team for specifics. And global teams can take advantage of our global enterprise license option available in most countries. And virtual reactor licenses can be served either on-premise or on the cloud, which opens the door to using both your own hardware and cloud computing resources. If you're a Barracuda user who would like to add license tokens to your RLM server in order to run more simulations or take advantage of the speed of multi-GPU, please contact our sales team. It's easy to add solver, chemistry, and/or GPU tokens at any time to meet your needs. We also offer engineering services for those of you with a one-off or urgent need, or if you'd like to gain the engineering benefits of modeling your system with Virtual Reactor prior to building out a team to run the software. And contact us if you want to learn more about this option. And the easiest way to get started is with our training classes. Our next class is coming up in July, and more information about that in a few slides. Training can be combined with project work and licensing in what we call our Quick Start program, which is intended to get you up and running as quickly as possible. We run the first models for you with our engineering services team, and then we hand the models back over to you, train you on the software, and provide the software licensing. And this allows you to build out your own in-house capabilities with models that are already up and running. And lastly, we work with people in a variety of custom ways through various R&D partnerships, ranging from fluidization research to researching new physics models to technology development. R&D partnerships can be direct with us or collaborative with our strategic partners. So contact us if you're interested in becoming a partner. We have some upcoming events that we would really like to highlight. PSRI's TAC annual meeting is in Chicago, June 17th through 19th, and several people from CPFD will be attending, and we would love to see you there as well. Additionally, members of the Global Barracuda Virtual Reactor user community attending the PSRI meeting are encouraged to stay for Barracuda Virtual Reactor Users Conference 2024, which is immediately following the PSRI annual meeting in the same venue. And CPFD is very excited to have our users conference June 19th through 21st. There will be presentations from Barracuda users, opportunities for networking, breakout training sessions, and plenty of good food. We've even scheduled a dinner cruise on the Chicago River that you won't want to miss. The conference presentations will span a wide range of topics such as refining, cement, hydrogen production, and cloud computing, just to name a few. And we are honored to welcome speakers from diverse organizations including Chevron, Cemex, Oak Ridge National Laboratory, and more. So register now and join us to see what's new and connect with virtual reactor users from around the world. And if you are interested in attending a web-based Barracuda training class, we have two options coming up in July and August. So contact us if you'd like to attend, learn about Barracuda in depth, and get some hands-on experience using Virtual Reactor. Finally, we invite you to visit with us at TC Biomass 2024 in September, where CPFD is proud to be a silver sponsor. You can check out our events calendar for more details on these and many other upcoming events. And if you have an upcoming event that you'd like us to put on our calendar, please send us that info. Okay, so now I believe that we are ready for questions. So be sure to add your questions in the box if you haven't already done so, and we'll get to those. And now I will start with asking the questions, and Sam will answer them.
Excellent. We're ready.
Yes. Okay. Our first question is, what differences are there between the rotating and time-varying gravity features when compared to things like rotating internal structures such as like propellers or mixing blades?
Okay, yeah. So, yeah, this is a good question and something important to be aware of, because I know that some users do have reactors that have internally rotating propellers, as opposed to the entire domain rotating. And so the rotating gravity features will not enable that rotating geometry within the system. So just be aware of that. Really what we've enabled here is that the entire domain is moving according to some variation in the gravity vector, rather than the walls of the domain moving relative to something inside the domain, like an impeller or a mixer. So yeah, just be aware of that. And we do know that that is a feature request from users, and so our development team is aware of that, and we're trying to think of what is the best way to really implement that. But that's not what this rotating gravity feature does exactly. Yeah.
Okay, thanks. And our next question is, does monitor run work for batch runs also?
Oh, okay. Yeah, so
just single ones?
Yeah, so this is an interesting run, right? Because the way that we have designed monitor run is that it has the assumption that you have a full GUI environment, right? That you have the Barracuda GUI open and that you're able to launch the TechPlot GUI directly on the interface that you're using. So there may be some way to get monitor run to kind of work on batch mode, but that's not the exact intention or design right now. It really is kind of geared towards people who are launching Barracuda in a graphical environment and kind of monitoring that run on that same graphical environment. However, for anyone who's interested in doing kind of batch monitoring, please contact us, because I think there are ways that we could kind of get a similar result by either using Python scripting or TechPlot in batch mode or things like that, right? Because there are options for kind of off-screen rendering of plots. So there may be some opportunity there, but this initial implementation of monitor run kind of assumes that you're working in a graphical environment and running the simulation right there in front of you.
Okay, yeah. And so we had an additional question come in right there that someone says, can you monitor a run that you started at the command line? So that kind of comes back to like, yes, you should be able to, but you might need a script.
Right. Or if you've started that, if you've used the command line for some reason within a graphical environment, like let's say you're using Linux and you've SSH'd into a remote machine to start your run from the command line, as long as you can access the directory in which the run is running, you should be able to also access the files that TechPlot needs to see. So yeah, I think that would be an easier case, is if you're kind of using SSH and you're able to access that file system.
Yeah. Okay, great. Yeah, so another question is, would you recommend the directional momentum feature for fluid beds that are trying to push particles in a similar direction using the gas flow? For example, a rectangular fluid bed dryer.
Okay, yeah. And there's a little bit more qualification there, or is it meant only for like stagnant piles of particles? So yeah, I would recommend that you try this feature for any system, right? It doesn't have to be a stagnant system. We've seen that it has nice physical results for things like those sand piles. However, we've also seen that it has nice effects for fluidized beds. So I don't think there would be any downside to using the directional momentum feature in a general case, right? Like using it for a fluidized bed or using it for a transport pipe, right? If you have like a riser or I guess it may not do much for risers because those might be more dilute. But for like dense pneumatic flow, I could see that it might have a really nice benefit there as well.
Okay. Yeah, we have one more question asking kind of similarly about the particle-to-particle conduction model. Like, when should you enable that model, and how do you know if you need it in your simulation?
Okay, yeah. And as I mentioned during the presentation, I think that for most people, if you have a well fluidized bed and the particle-to-particle contact time is relatively short, then I don't think that particle-to-particle conduction is going to be a very significant mode of heat transfer in those types of cases, right? I just don't think from a physics perspective that it would be likely to be important. However, if you have something like a packed bed or something where the particles really are closely packed for long periods of time, then I think using that model could add an extra level of fidelity to what you've been doing.
Okay. All right. Well, I think that's all the questions that we have right now. And so I think we can end this webinar at this time.
Yeah, thank you all for attending. And feel free to reach out to support@cpfd-software if you have any questions at all about these new features. And we look forward to getting your feedback on them. Yeah. Thank you, everyone.
Thanks.